Okay, on this fifth day of our working through constructions and geometry, we're going to talk about the circumcenter of a triangle. The circumcenter is the point where all three perpendicular bisectors meet. So let's go ahead and make some perpendicular bisectors for each of these sides and see what happens. So remember, when we are making a perpendicular bisector of a line segment, we want to stretch our compass out to go a little more than halfway across that line segment to make sure our arcs are going to meet each other. If we don't go far enough, we'll end up with a gap between our arcs. Let's see how that works. Go to the other tip. Oh yeah, that's good. Okay, there's one. So I'm going to come along with my pencil on the straight edge and connect those. Try the next side. I think I need to shorten this up a little now because this side isn't as long as that bottom one was. This tip. My 2 points. Now remember, this point and this point are both equidistant from those endpoints. So when we connect them, we should get a perpendicular bisector because we're kind of making the altitude of an isosceles triangle that goes through there, remember? Let's try this third side. Maybe a little wide still, not much. Okay, go to one end of my line segment, make my arc, go to the other end, make my other arc. Make this one show up good right there. Okay. Same thing my students do all the time. There we go. And ta-da! That worked out perfect. Look. Okay, all three of my lines line up exactly right there on that point. That point right there, where all of my perpendicular bisectors meet, is my circumcenter. Okay, what does the circumcenter theorem tell us? The circumcenter of a triangle is equidistant to the vertices. Well, we didn't do anything with the vertices just then. We bisected the sides. So what does that have to do with the vertices? Well, let's see what we can figure out here. So if I'm going to go from this circumcenter to the vertex, let's do all three vertices. there we go. Okay, so our theorem is telling us that this purple line, and this purple line should all be equal. Let's see why that would work. Okay. If I look at just this bottom triangle here, this really wide and short one, my perpendicular bisector is the altitude of that triangle, right? Okay, and so that means this side, this is cut in half. That half of the line segment and that half of the line segment would be equal, right? Okay, and this is a 90-degree angle. So I have an equal angle here. I have equal sides here. This side, of course, is equal to itself. So I have side angle side. So that means I have two congruent triangles. So that means this side is equal to that side, right? Okay, well, if I look at any of other two triangles, same thing. This is the perpendicular, that is the altitude of my triangle. And also this part of the line segment is equal to this part, because remember that was a perpendicular bisector. That means we cut it in half. Each side is equal to each other. So again, what do I have here? I have side. If I look at this triangle compared to this one, I have a side, I have an angle, because they're both 90, and this side is itself, so I have side, angle, side congruency here. So that means that this side has to be congruent to that side. So what have I ended up with? This one, and this one are all congruent. That is what our circumcenter theorem says. We just proved it by looking at each of these small triangles, proving that they were congruent, That proved that these distances from the circumcenter to the vertices of the triangle are all equal. Okay? So now I'm suggesting that we kind of look at this backwards. I'm going to draw a pretty decent sized circle on here so it's big enough for you guys to see and big enough to work in. Put my center here and do a decent circle. Okay, we're going to draw a big circle, and we are going to pick 3 points anywhere on that circle to be the vertices of our triangle. Okay, I've drawn my triangle inside of my circle so that all 3 vertices are on the circle. Now we're going to construct perpendicular bisectors of each side of the triangle and see what happens. Okay. Same process again. The This is my line segment. If I'm going to create a perpendicular bisector, then I need to set my compass to go a little more than halfway across. I'm going to put my tip on the end of that line segment. Put my tip on the other end. Remember, why am I doing that? Because I'm trying to find this point and this point that are both equal distant from there. When I connect those, it's almost like I'm connecting the altitude of two isosceles triangles stacked on top of each other to make sure that it cuts through at a perpendicular. So my lines will meet up, right? Okay. Do the next side. Not long enough, let's stretch it out a little. Okay. There's my circumcenter right there where all three of those perpendicular bisectors meet. And here's the cool thing. Look at from that point to this vertex, from that point to this vertex, from that point to this vertex. What have we made? I can feel with my finger, maybe if I pressed down hard enough with the tip of my compass when I was making this circle, I can feel with my finger and see that that distance is the radius of my circle. So when I drew my original circle, guess where I put the tip of my compass? I had it on the circumcenter. Once I did all those perpendicular bisectors, found the circumcenter, I could feel that that was the original center of my circle. So that just proves again that the distance from that circumcenter to the vertex is the same for all three vertices because it is also equal to the radius of my circle. Of course, those are all the same. They're the radius of the circle. Okay. The next thing we learned today is what is an incenter. What's the difference between the circumcenter and the incenter? Okay, so remember, circumcenter is where the perpendicular bisectors meet, and it is equidistant to the vertices. Now, incenter is the point where all the angle bisectors meet. So we're going to try the same thing. We're going to find the incenter on this triangle. Let me refresh your memory. How do you do an angle bisector? You need to go put your point of your compass on one of your vertexes, on one of your vertices, let me say it properly, on the vertex of the angle. And I'm making a little arc. The only reason I'm making this arc, the whole point of it, is so that I can find this point and this point. those are both the same distance from my vertex. The reason I want that is because now I can go from those points, I'm going to shrink this in a little, to bisect that angle. If you watched my video from the day we learned angle bisectors, we drew a little isosceles triangle in here, and we saw that if we wanted to do a perpendicular bisector through the base, that it would also bisect that angle. And this is the method we used. Just to refresh your memory on why this works. Oh no, I moved it. Sometimes you let it shift and it messes you up a little. Alright, let me try to fix it. Hopefully I can get these all perfect and they will meet in the middle like they're supposed to. Alright, I'm going to this vertex, drawing an arc, going from there to make my angle bisector. Probably should have gone a little bigger. It's more accurate. You're less likely to get a little crooked with your line when you give yourself more room. I'm going to go bigger on the next one. I made this one kind of smallish. Okay, let's see. I think that looks good. I hope so. Last angle. Okay, I made my arc, so that gives me my 2 points I'm going from to find that bisector. Keep our fingers crossed. Oh no, I don't think they're going to line up at all, are they? Well, it's not perfect, guys. It should be. This is just a testament to the fact that I got my angle a little crooked. It was probably that one right there that I made too small. I bet it's supposed to be a little more down. But anyway, we'll sort of average those together and we'll pretend that they all met and say that is my incenter. What does the Incenter Theorem tells us? Now we're going to prove that. The Incenter Theorem tells us the incenter is equidistant to the sides of the triangle. Well, we just went through bisecting angles. What does that have to do with the sides? Now we're talking about sides. Let's figure it out. Okay, so from this point, now I'm not going to get really technical and draw these with my compass right now, but I guess I could. The fact that I already have this thing off a little bit makes me a little less likely to be exact, but if I wanted to get my compass out and try to make a perfect altitude through there for you, I could. I'm trying to make an altitude going to each side through that incenter. I'm not constructing these because I'm just using these to demonstrate the proof real quick. If we wanted to, we could certainly construct them because we know how to create a perpendicular that runs through a certain point. Okay, here we go. Let's look at each of these smaller triangles here. All right. These are all angle bisectors, so that means this angle is equal to this angle. That means this angle is equal to this angle. And that means this angle, 2, 3, is equal to this angle, 1, 2, 3. That's the definition of an angle bisector. We cut it in half. Each of those angles are equal, right? Okay, so now if I look at this small triangle here, I've dropped an altitude. So I know this is 90 degrees. I've dropped an altitude here. I know this is 90 degrees. So I have an angle. If I look at these two, ignore the rest of this for a moment. Look at these two triangles. I have a 90-degree angle. I have a 90-degree angle. I have this angle is equal to this angle. And I have this side is, of course, equal to itself because it's itself. So what do I have? Angle, angle, side. So these two triangles have to be congruent. So if this side is, that means this side has to be congruent to that side, correct? Same thing if we turn and look at these two triangles, ignore all the rest. This angle is congruent to this angle. This angle is congruent to this angle because they're both 90 degrees. This side, which is like the hypotenuse of your little triangle, is congruent to this side, the hypotenuse of that triangle, because it's itself. So I can see that this triangle is congruent to that triangle, which means this leg is going to be congruent to that leg. What did we just show, guys? We just showed the proof. When I looked at all these congruent triangles, I found that this length from the incenter to the side is congruent to all three sides. Fantastic. Another way you can prove it using constructions is to take your point, put it on your incenter, measure out the length to that. Now, again, I would have had to make a perfect construction of an exact altitude to make sure this came out right, and I would have had to have my incenter perfect, which I didn't quite do. If I had all that lining up, pretty close, I should be able to make that distance from the incenter to the side of the triangle the radius of my circle. And that circle should fit perfectly in there, proving that each of these distances is the same because they're all the radius of the circle. So when we're asked to explain that the incenter point is equidistant to each side, we can write our proof of how we used congruent triangles to find that these sides were both congruent. Therefore, all of the distances from the incenter to the side were congruent. You could say to further prove it, we saw that we could draw a circle, and those were all equal to the radius of the circle that touched the sides.